Hello everyone, this is Soumya Prasad. I'm an undergraduate student from Yale University pursuing my BTech CSC Honors with AI and IP as my specialization. Today I'm here to explain the topic LRU cache. I'll give you a quick introduction on what LRU cache is and we'll discuss what kind of problems LRU cache solves. We'll see how LRU cache works. We'll see how it is implemented in real world. We'll see a pseudocode for it and we'll actually code it in Java, and then we'll look into a lead code problem with the same topic. Yeah. So what is a cache? So a cache in computers is a small, fast memory component that stores frequently accessed data or instructions for quick retrievals. It acts as a buffer. So let's say this is our RAM, this is our processor, this is our cache. This acts as a buffer. Why? Because slower main memory and the processor aiming to reduce the time and effort required to fetch information. So processor here is much faster in execution than the RAM. So the RAM needs compatible storage so that it can accelerate its executions. So some of the most recently accessed elements you will store in a cache, and then the processor may use it to quickly access it, update it. Right. So what exactly is LRU cache here? So LRU stands for least recently used cache. So least recently used cache is a powerful data structure in the computer science field which optimizes data retrieval and storage. LRU cache has lightning fast access to frequently used items while discarding the least recently used elements. It has high performance over other caches. So let's quickly get to an example of how it works. Let's say this is my RAM. This is processor. This my cache. And additionally, I will maintain another data structure which will store information about the elements here. It will store their addresses. So this stands for RAM, processor, cache. Say it's a set. So let's say the processor asks for element 1. First element was 1. So element 1 will immediately be stored in the cache. Key value 1, address of this node, and since the cache was empty, it got inserted into this place. This place we'll call this the most recently used element. Okay. Next element comes in 2. So now processor will again check if we have the element 2 over here. Do we have? No, we don't have it. We'll add it here. We'll have the address of it here. But now 1 has to be moved from the most recently used element because 2 is now the most recently used element. 1 has to move downwards. Move it. 1 was moved downwards. 2 is moved upwards. 2 here. And yes, it's done. So let's add one more element now. 3. We'll check if 3 is there. No, 3 is not there in this list. We'll add 3. We'll add the address of 3. And now again, 2 is no longer the most recently used element. 3 is the most recently used element. Automatically now, 1 will shift a position downwards. 2 will shift a position downwards. And this 3 will get added the most recently used element. Okay. 3 most recently used element, then 2, then 1. This is the least recently used element. Why? Because 3 was the most recently used element, 2 after that, and 1 after that. 3 most recently used, 1 least recently used. Alright, up until this point it was very easy, very clear. Now, what if new element 5 occurs? You can very clearly see that the capacity of my cache is only 3. It cannot hold more than 3 elements. But now we have 4 elements. What do we do? Since the capacity of my cache is 3 and it is already full, we'll have to remove one of the elements. Which element would it be? It would obviously be the least recently used element. The element that was used least recently. It will remove this. So first we'll remove it from the set. We removed it from the set. Then we remove it from the cache too. And this element got entirely removed. Now about the new element, 2 has to move in position downwards, 3 has to move in position downwards. Let's do that. Move 5 is now the most recently used element, right? And before we insert here, we'll have to store it that this is the key and this is the address of the node. Now, if the processor asks the key value of 3, then we'll check it here. Do we have 3? Yes, we have 3. Do we have the address? Yes, we have the address. Where is it? Here. The processor will take the value and do its execution. But now we are responsible to change the position of 3, the most recent one. Because 3 is the most recently used element now. What has to happen is 5 was the most recently used element, but it has to come down. 3 has to be moved upwards. You can see they just swapped their places. So very accurately, 3 is now the most recently used element. 5 is no longer the most recently used element, but still. Okay. This was an example of how LRU works in a very short and simple manner. Okay. Alright, let's dive a little deeper into this. So, how do we implement the LRU cache? We implement it using you see a doubly circular linked list and HashMap. The solution combined by these two data structures lets us have very efficient solution. So, for example, HashMap lets us rapidly look up these items, and doubly circular linked list maintains a perfect order. Perfect order. We'll be using the combination of these two to more accurately. The cache is represented as doubly linked circular linked list, right? This is what double circular link looks like. This represents a cache. The cache is represented by a doubly linked list where each node in the list contains key and the value pair of an item. The linked list is arranged in a specific order that reflects the access pattern items, with the most recent one being the front and the most least one being at last. And we have an HashMap. Why do we have HashMap? In the example I told it about it as a set, but look at it here. The HashMap will have key and a value pair. Key will be an integer. The value will be a node. Which node? The node of the linked list. Node of the linked list. Let's say 3 address, 2 address. To facilitate faster retrievals and updates, a HashMap is used along the linked list. The HashMap stores the keys as the dictionary's keys and corresponding nodes addresses. This enables fast, efficient lookups. So if the processor asks, get me the value for key 3, we just fastly come over here, we have it, return it. That's it. Simple. Alright. Now let's also look on some other perspectives. Now, why did we specifically use a double circular linked list? Why just that? I'll explain that here. So why did we specifically use it? You see, a doubly circular linked list, removal and insertions are very easy. Why? Insertion from both the ends. Let's see why. See, if I have the head node, just the head node, I can easily get the value of the last node. How? Just by using head.previous. I can access the last one node also. How? dot previous dot previous. Very easy. But if it were not doubly linked, I would have to traverse all the way around to the last node, use the pointers to get there, use a while loop to get there, and that would be a lot of operations that we did not want. So a doubly linked list allows us for constant time removal and insertion operations. This is crucial for quickly updating the cache when new items are accessed or the cache becomes full. Let's say if I have this node in the linked list, I can quickly access the neighbor elements very easily. This would be the previous element and this would be the next element. If ever I had to delete this element, I would simply join these two elements. Very easy. Deleting this element, or if I were to add anything at the head, that would be easy too. I have the previous pointers, I have the next pointers, that would just make it so easy. And combining all of this in a double linked list, maintaining specific order becomes very easy. Agreed? So in the example I showed you that if any node is called upon by the processor and it is already present in the cache, then its value will be changed and then it will be moved to the front. Let's say this is the head, it will move to the front. Now, inserting an element in the middle of two elements is very easy, because otherwise if in case of single linked list, you would have to traverse through it, find this element, traverse back, find this place, and log. Right. Why do we exactly use a HashMap? We exactly use a HashMap for fast lookups and retrievals. I showed this earlier, but I'm doing this again. So if in the previous case I was to find the value at this node, I would generally traverse the entire linked list, use space, remember everything, how many times, if I were to calculate how many times it occurred, where it is, where the addresses are, how they are placed, that would take so much of space. But now I'm not doing any of that. I'll just use the HashMap. I can use hash table dot get function to get the value of this at this place. At this place. Very quick. This gives me it allows for constant time access. It eliminates the need for linear search throughout the double linked lists. Right. Now let's discuss what are the operations required in an LRU. So initially we gotta initialize cache with the capacity provided. Then there will be a function starts with get key, which you have a node with the value of key, and that then you can easily return that value, easily return that node or that value. But if you do not have it, simply return -1. And then we have put function or the insert function. If you already have the node or the key and value pair in your cache, you'll just update the cache with the value. If you say you do not have it, then you'll have to check the capacity. If the capacity is lesser than what we are storing in the linked list, then we have to remove the LRU and then add our new node. And in this case, we'll just move it to the head. I'll show you an example of this. So let's say this is the cache. HashMap. This doesn't have to be in this order, but still. Okay. Now the get function asks for the value of 2. I'll check in the HashMap if that key exists. Yes, that key exists. Then we go to the address of this. We find the value of this node. Return that value to the processor. Simple. Very simple. Let's say the processor asked for a value 5. We check it. It's not here. We return a -1 back. Okay. Now the next put function. Put 2, some value 10. Let's put 10. We first verify if you already have the key 2. Yes, we have the key. We go to the address. We update this value 10. Then we remove this from here and move it to the top, where it would represent the most recently used element, right? And that would become 2, 4, 3, with 3 now becoming the least recently used element. So let's say at this point of time we have 5, 5. We check if we have 5. In the HashMap, do we have 5? No, we do not have 5. Now we check the capacity of this HashMap. It is already 3. My capacity was 3 and now its size of the HashMap is 3 and my capacity for the linked list was 3. What you have to do is firstly remove the reference of the LRU from the HashMap. Remove the reference, create new node. Create the new node 5, key 5, value 5. So new value added 5, 5. This got deleted. Now it's more like this. Let's say for in an instance it's like this, but since we know we have to add another element, we'll add that newly created element at the top 5. These two elements automatically shift down. Now 4 is the least recently used element, 5 is the most recently used element. Now, all of this is very clear, it's very simple. You just have to follow some clear steps. So let's again look at it. If we were to get a value, we look up the element in the HashMap. If the element is present in the HashMap, it is stored in our cache and we do not need to retrieve it from memory. This means we had a cache hit. Remember the keyword cache. Then to mark the element as the most recently used element, we retrieve its corresponding linked list node from the HashMap and move it to the top, like we did here. If the element is not present in the HashMap, it is not stored in our cache. Like we did not find 5 here, it obviously was not here. So we need to retrieve it from the memory, and now that thing is called cache miss. If you did not find it in the HashMap, it's a cache miss. To make room for a new element, we may need to add this. We may need to remove the last element. We will check the capacity of the linked cache, and then if it is more than the capacity that we inscribed, we will remove the last element. We'll make some room, shift the elements downward, make the new element go up. Yes, that's all there is. Now let's quickly have an understanding of the pseudocode. The pseudocode says if the element exists in the HashMap, move the accessed element to the head of the linked list. Let's say the processor asks for the value 3, we'll have to move it to the head of the linked list. The new linked list, the new cache will look like 8 and 4 and 3 to 4. Else means the element was not found. That means the processor asked for a value that was not here, and now we have to remove an element because the cache is full. If eviction is needed, when is eviction needed? Eviction just means removal. If eviction is needed, that is cache is already full. When is eviction needed? When cache is already full, remove the tail element from the double linked list and delete its HashMap entry. Remove the LRU and delete its HashMap entry. Done. Add the new element at the head of the linked list and it's in the HashMap. Now with 5, we will store the address of 5 and then we'll make 5 the new head of this cache. Alright, this was all pseudocode there was. Now let's jump into the actual Java code of this thing. For this I am using Eclipse ID. I have a class ready with the name LRU Cache. We'll one by one code a lot of functions, lot of things with much clarity, much experience. Now, first we need to define a node of the type double linked list. So for every basic node we have value, node, pointer, next. But since this is a doubly linked list, we also have previous, and since this is the cache, we'll have a key also, right? I told you, single node will have a next pointer, will have a previous pointer, will have a key, will have some value. The address of this is stored in HashMap. HashMap has key and value, key, this key, value, address of this node, right? So let's define our HashMap. In Java we write hash table integer and then node, we name it cache new hash table. Same thing in let's make the scope private. Let us not allow anyone to access. I guess we have to import that. That's all. Now we also got to define our capacity. Then let's also define a head node. And one more thing I do is I also define the tail node. Many of them do not do it, but it's for it, I feel it's more convenient to do so. And another thing that I do usually is I take a count variable here so that I can keep track of. So how do you know that what is the size of your HashMap? You can just use HashMap dot size, get the size instantly, or just use a count function every time to count it. This seems more simple, understandable. This is simple too, but I follow this. So we, as discussed, we have public a constructor which takes capacity. We'll write the code later. And then we have a get method which would get us the value, which would give us the parameter. Then we have a void put method which would bring in key value pair and return nothing. Okay, let's start with initializing our constructor. So initially the count must be 0, capacity is capacity here that we took. and then we have head. So add a new approach. How I follow now and this. I'll always have a head. I'll always have a tail. By default, this is the case. The head, tail. I'll link them up. Previous, next. I'll always have them, and in between, if an element comes, the put operation is up, then the new element will be between these two. Right? And dot previous should be null as of now, and tail dot. Okay, d dot tail is good. Yeah. Tail, but tail dot next should be null as of now. We got to update it head dot next tail now, and tail dot previous head. Yes. So our constructor is done. Now get. So as discussed, in the get method, we'll take integer e. If that e is present in the hash map, then we identify the node, move it to the head, delete from here, right? If it is not there in the hash map, then we'll check the capacity of this. If it can fit in, we'll directly move it to the head. If it cannot fit in, we'll remove the last element. We'll remove the least recently used element and then fit in. That's for the add case, but yet if you do not have the element, we'll just have to return -1. And return -1. Okay, method. Okay, let's code it. So let's say node is taken. This returns node if it has one. If it doesn't have one, that's one. It's obviously null, and if it is null, we simply return -1. But if there is a node, we will have to move it to the head, and Excel will just write a function separately to do that for me. For the timing, I'll just write this. After the head is moved, we again return this. Simple. So, that says we are not done with the move to head function. Okay, we'll get done with the move head function now. Let's make it private because no one else should use it. Void move head. So when do we move it to the head? We already have this element. We get this. We update its value in the hash map. Remove it from here and it to the top. That's how to do it. First, removal is important and then addition. First, we can remove it, and I'll write a function to remove it later. Okay, nothing. That's it. We'll keep it the node. Can remove that node and addition also let me write another function because later I'll have to use it for other purpose. Alright, remove the addition. Let's write add function in private void add node node node. Okay, now we as discussed when we're adding that node we have already deleted it. Delete is the execution of another function, just another separate thing. Just focus on addition right now. Let's say this is the new node here that needs to be moved in here. First, this is the head, and it has connections this way. It was connected with this. Next, connected this way. This is the tail. Alright. This needs to go in there. So we have to move those two connections. Firstly, head dot next should be this new node, and then this new node dot next should be heads next, right? Heads next should be this new node's next now, and this new node's previous should be this node, and new node's previous should be head. So more clearly, if I say previous head dot next will have to first change new node dot next to previous new node dot previous to head, and then head dot next should be the new node and the second node, that is head dot next dot previous should be the new node. We'll code this down. Node dot previous head node next head dot next, and now the head dot next dot previous node head dot next node. Clear. Now let's write the private void remove node. Let's take this diagram. Let's say we have to remove this node. What do we got to do? Let's say 1, this is 3, this is 2. But I remove the second element. Then this connection is no longer needed. This connection is no longer needed. Thus, this. We got to connect 1 to 3, which means 1 dot next should be 3, and 3 dot previous should be now 1. Alright, this 4 connection is gone. Then we remove that, and the new connections were established. And in code, this is how we write it. So first, node previous, I am taking a variable of previous node, previous node or previous, whatever the previous node was, we saved it. Next node is, we are saving that too, and now previous dot next is equal to next. See, previous dot next should be the next, and next dot previous should be the previous, and next previous. Yeah, we are done with move to head function, and we are entirely done with the get method. Let's start with the put method. Put is nothing trickier, it is much easier. So put method takes two parameters, key and the value. You gotta make them a pair. If it exists, just update the value. Exists in the HashMap, just update the value. Doesn't exist in the HashMap, create a new node. Node or just add. We'll just call the add operation, and here we'll call the move add operation. Right. Let's do it. Node cache get key. If there was no key, that means node will be null. Then let's do something, or otherwise, if the key was found, then simply as data will update it. Will update it with a new value. And move this thing to that. Yeah. And what if it is not there? If it is not there, as it will create a new node. Okay. Not write any specific constructors for that. So we find we cannot put the value is to be assigned. Now we check the size of my HashMap is greater. We have to pop out last element. What is last element? The tail. Okay, not this one. Okay, we did not write how to remove the last element. We'll write another function for that. That would be much cleaner code, much understandable. So inside this if condition only, we'll write this dot cache dot remove from the HashMap the value of the key. Remove. Now count wave can be decreased. After it has decreased count variable, which means we have enough space to incubate the new node. Now we add the put new key with node's address. Then after it, add that node. Remember, for add new node function directly adds the node at the head. Alright. Yes. Remember always to store the address of the new node first and then add it to the linked list. Okay, we have not done with writing the bobtail function. Let's get done. Very small function. Write it with the remove function. Private again because we do not want anyone to access it. Private, not void, because there I wrote have to get that node top field, no parameters, void. Yeah. Now node answer for field address and remove this node. Yes, that was the node and returning this. Returning the so if this was the head, this was the tail, this would be the least recently used element. This would be the most recently used element. We never delete the tail. We always delete the tail dot previous element because this is the least recently used element. This we are maintaining just for the convenience. That's exactly what I wrote there. We are accessing the tail dot previous element, sending in the remove node function, which will absolutely take care of it and return us that. Yes, so we are pretty much done with the code. Lead code follow the same constructor, the same get method, the same put method. They give you this input output. Yeah, very less to do. The main function has already handled all of this, and you'll just have to write these functions. That's it. Sure, you will understand this after reading once. And the language Java. I think we can paste our code. Copy it. Yes. It's okay. So thank you for listening to this, for being patient.